Okay, thank you, Veronica, for the introduction. Good morning, everyone. And this is actually a two-part presentation of the way we see the smart grids application in Chile. The second will be done by Guillermo. And the context of my presentation will be first give you an introduction of how we see things in Chile regarding the smart grids and the potential we have for this. And the second part of the presentation will be, the second point actually would be to show you the microgrid in Huatacondeo. It's a small village in Chile, and how we actually carried out the project there. We built a small, very small, but still it can be seen as a microgrid, and that is running as we speak. And then I will show you a project that we have. It is in the final state. It's a plug-and-play micro-hydro unit that we think that it has a lot of potential for applications in microgrids and in rural electrification in Chile. And then I will give you the conclusions. Okay. So first, I didn't know that we were in family, so I prepared this to give you an idea where is Chile. Okay. So this is for the German people, that Chile is a very, very long country. It's about twice the size of the surface of Germany. And but we are not so many people. We are 16 million people, and this is just the people that lives in the central part of the country, 6.5 million people. But in the total in the country, we are 16.5. Okay, and this is the peak load in the central part of the country, and we are nearly 5,000 kilometers, and we are mainly hydro in Chile. 65% hydro, 35% thermal. The non-conventional renewable energy installed capacity in 2010 is actually 600 megawatts. It's very limited. We call non-conventional just to separate from the big hydro. As I told you, we are 65% hydro, but this is just a small hydro that is less than 40 megawatts. Small projects. That is small hydro for us. And we have wind 168 and biomass 218. That is what we have so far in the country. But we have a lot of potential. I will not show you here the potential, but we have, in terms of wind, we have several thousand megawatts of potential, a long coastal line. We have many rivers along the country, so we have a huge small hydro potential, and also biomass. We have industry and wood and pulp and paper industry, etc. So I'm going to present you Huatacondeo. What is Huatacondeo? Huatacondeo is a very small village located in this part of the country here in the north. And in this part of the country, as you may know, there is a huge desert. There is nothing in there. It's completely dry. Actually, it's the driest desert on earth. I was told, and I have seen pictures, that is the only part of the planet that you see that is not blue, completely blue, because our planet from the sky, you see it is blue, but in the solar desert is brownish a little bit. There is a small dot brownish, because the sky is very clear as well. We don't have clouds or anything that. And for that reason also, I want to tell you, there are many astronomy projects going around here. A lot of observatories. The European Southern Observatory, for example, has many installations there. Well, anyway, coming back to this, this is a very small place, but it was chosen because we think that we didn't have any experience at all in Chile to build an actual smart grid, or to do some integration of different resources of energy into one single grid. So These people is small. It's a very small village, as you can see. It's 80 people, roughly 23 families. But they had only a diesel generator, that would work for some hours per day. And we wanted to undertake this project in the following fashion. We wanted to make an integration of different technologies, and to use what they have. And what they have is basically sun and wind. So we wanted to integrate sun and wind into what they already have in the electricity production, which is just one diesel generator. That was the project itself. So this is more or less the outline of the project. We have here in the lower part the generators. The generators are PV units. Also, we have a wind generator, and here is what they have already is the diesel tank and the diesel generator. And we came up also with a storage system made out of battery, 600 V, 40 kilowatts. And we had to supply the demand of this small village, which was basically housing and a water tank for water consumption that they have. So we have to feed the water pump. And this is the general system that was designed for us to supply the energy in this. We see that even though it's small, it has all the ingredients of a smart grid, because it has several different units of generation. It has a storage here, and also it has a demand here. And also we came up with the demand side management interface that is going to be explained in detail by Guillermo, that it is related with the concept that Hans just showed us. And all this is integrated in an internet framework as an SCADA, and actually we can see it from, this is roughly more than 2,000 kilometers from Santiago. We can see it daily in our screens in the University of Chile. And this is how it looks, the constructions of the PV. We have 22.68 kilowatts. There are 84 PV panels, and we had to choose the locations and see what was the best location inside the community. There you can see the community there. And this is the amount of power that we have per square meter in there. Very simple concepts, not too complicated. We try to keep as simple as possible the project. 2 linear actuators, no sensors, centralized control. We just keep it very simple. No. We didn't use any other type of control here. For the storage system as well, we use just a set of batteries with capacity for charge and discharge. Of course, we remote telecommunication unit for getting the information. We use the inverters here is a base of IGBT technology, and is the capacity of 40 kilovolt ampere. This is another interesting part of the project. The wind generator has to be protected, because this is the name Huatacondeo means actually a place of condors. Condors is a big bird that is over there, and these big birds are a part of the system. So we had to protect the wind generators, so not to they don't kill the animals, they don't kill the birds. So they had to build this sort of a nest here in front and in the back of generator that you can see it inside there for bird protection. Well, this actually, although as I told you, although it's not big, but it has all the ingredients of a complex system. We have to set up an energy management system that has everything from, for example, we have to measure the data, we have to measure what it is being generated, what it is being consumed. We had to have a sort of prediction for the weather forecasting, and with all this we had to do an optimization unit commitment to decide which units will be running. We have to do an optimal power flow in terms of getting the less expensive way to produce the energy, and also we came up with the demand side management system to tell the people when they had to start reducing their consumption. We designed all this, and is as I told you, is currently running. And also a very important part is that because these people live there and they are not, it's a small village, they have to be part of the project as well. It's a very strong part of the project is how people actually interact with these things, and particularly here in the demand side management, how the people has to understand and have to be able to read when they are increasing the demand and when they have to decrease it in timely. So there was a lot of community works, seminars with them, and many hours were spent in explaining and trying to let them be part of the project. And the operation data we had in this system is in here. This is a particular day. We have demand, we have generation, and we have all the ingredients here to take a look on what's going on in the system. This is the time. This is 24 hours and active power. Okay. Now we're going to talk just a little bit about the microhydro. The microhydro is, this is the share in Chile of conventional hydro versus small hydro, very small as you can see here. Again, the aggregated capacity here between 400 and 800 megawatts. It is most of the installed capacity in the country and very limited in the small range here. So we don't have that much small or micro hydro. With all the hydro is basically from above 100 megawatts in the country. But on the other hand, we have many people that lives in rural areas, and they use either they connect from the electricity, and it's very expensive for them because they are far away from the main distribution companies, or they had their own diesel generators, or they even they own small rivers, or they own the rights to use the water, so they have the capability to build small micro central units. So we want to use this capability that they have to start up with this idea. Some numbers here are roughly 25,000 rural houses are without electricity in Chile, 10% with hydraulic resources, and that leaves us with more than 2,000 potential customers that we have. So the idea for us is to design something like this. This is actually a real comparison. Small unit that be modular, that you were able just to tap in the water and produce energy. That is the idea. And this is the design of all it has to be modular, very small here. It has to have I didn't translate that part, but it has to have a pipeline system to channel the water, and there has to be some civil construction. All this project involves civil works, and you have to build some channels, you have to build pipelines, you have to build some valves in order to control the flow. And it has to be fully automatic, and it has to have the possibility when you don't have, for example, electricity in the grid. Well, you should be able to operate alone, and if you have the electricity, you have to be able to produce in a combined way, and so on. And it has to be also sensitive in terms of money. It has to be competitive with the alternatives. And for example, the first condition is that it has to be able to operate without a grid interconnection. So if I live far away and I have no possibility to a grid connection, and I build the system has to work. The system has to be able to supply the necessity of the people. And also, when you are in the house and something happened here, and there is a blackout, for example, something happened, and you disconnect from the grid and disconnect also from the turbine, from the micro hydro plug-and-play unit, you have to be able to reconnect. To do this reconnection here is quite simple, actually, because you just turn on the switch here, so this is no problem at all. But this one here is a little bit more complicated, because there is a turbine here running and a generator and so on, so it has to be synchronized. So that capability also has to have it. So you can, this here is very simple. You can just switch it on, or you can do the synchronization here from the micro hydro to the electrical grid here. And also, of course, the three interconnections has to work without any problem. It can sell energy to the system, and it has to have also a good or better human interface. It doesn't have to be difficult to operate. It has to be very simple, because this has to be operated by regular people. You don't need to be there. So people that actually work in the land, rural people, they have to be able to just plug in and press buttons, and the thing should start working. Well, here is just to show you what the pipelines are, our concepts, foundations, and well, it has to be easy transportation, of course, and easy to move, not so heavy, and it can reach anywhere. We put wheels on it, so you can move it. And this is the concept for the pipeline to sand filter and charge chamber, and the barrier for fluid water control here. Well, this is how it looks, the unit so far that we have built. This is just in the level, in the last stage, as I told you. We have proved the concept in the lab. It's already working in the lab. When you visit Chile, we took you there, so you could see the machine working. And now we have to we are in conversation with a small group of people that use water in rural areas to find a place and to actually build one unit and work it as a demo unit. We run some numbers just to give you an idea here. What are the alternatives? Grid connection by using diesel generator, micro hydro, and using the smart micro hydro plug and play unit. These are the numbers here. We came up with this cost in 5 years. I'm sorry for the cost there. It has to be cost without the O. Okay, so according to the preliminary numbers we run, this is very competitive with the other alternatives in terms of cost. of course, which is our ultimate goal, is hopefully to target the retail, to be able to put this thing in one huge home center or easy or wherever is selling these units, and so people go and buy it and go home and plug and play the unit. Some further developments we see, it would be a nice idea in the future, of course, this is for future ideas, if you have many of these systems along the country, to somehow do something similar to the project that we just saw in the previous presentation, that to do some coordination with all these units or all the demands, but we were thinking just about the generator part, not the demand part. In the generator part, and to have something like a virtual generator with all these units although they are separated geographically, but they can be coordinated as one unit if possible. Okay, I'm coming to the conclusions now. We have two applications of smart grid technologies. We have one in Huatacondeo village, which is a very small project, but it has, as I told you, all the ingredients, and it has a huge potential for duplicating in all isolated communities in the country. We have produced an energy management system that is quite operational actually, and is working very, very nicely. It does the work, and it reduces, which is more important than the consumption of diesel, in 50% approximately. And for the micro hydro plug and play units, it can help rural electrification, and we think that it has a lot of potential. It could be a very competitive alternative for people living in rural areas. Okay, that's all I wanted to show you. I don't know if you have. Okay.
Well, good morning to you all. Thank you, Veronica, for the introduction. As Luis said before, I'm going to somehow continue explaining and showing you all the latest developments that we have achieved so far concerning microgrids applications. In my case, I'm going to show you an explanation application dedicated to microgrids, basically isolated microgrids, which is the social SCADA approach, which is a concept that we are proposing. And we believe it's a very useful tool for the operation and maintenance of microgrids in isolated locations. This work this is part of the contribution of too many people, because we always work as a team, so I'm just showing a bunch of people who has contributed to that item. Okay, the agenda is just basically one background, the real challenge that appeared when we faced the problem of the microgrid application for isolated communities. And later then I'm going to show you a description of the social SCADA system, and of course by the end I'm just going to show you some conclusions we have achieved so far. Well, background, it is useful to begin to talk about the smart grids, and in that sense, you know, smart grids arrive because we have identified three specific factors that have promoted the appearance of the smart grids. So first of all, there are some new power electronics advances, computators, processors, telecommunication systems, and actuators. Secondly, we have the increase of the complexity and requirements of both energy markets and also the power networks by themselves, reliability, flexibility issues. So we have to consider that. And later then, we came up with the integration of renewable intermittent sources, distributed generations, electric vehicles, and all that stuff. So basically, when all those things appear, we have like some kind of umbrella concept, we can call it that way, which are the smart grid solutions. And behind that umbrella concept about smart grid solutions, there are plenty of solutions that are dedicated to that issue. We have massive integration of renewable energies, virtual power plants, smart meters, smart houses, buildings, and of course the microgrids. On the other hand, we have the SCADA applications. An SCADA system is basically a supervisory control and data acquisition system, which is a computer system for gathering and analyzing real-time data. SCADA systems are used to monitor and control a plant or equipment in industries, and there are some standard applications of SCADA systems. I'm going to show you just two applications. The first one is, for example, the example of a distribution company. They have already their SCADA system, so it means that in real time they are monitoring all the some specific variables in real time operation of the system. There's a guy located in the control center of the distribution company with a huge monitor looking at the operation of the network, and suddenly it appears some failure on the distribution system, so this guy is going to receive it might be a call from someone user of the distribution company, a final user, and also he is going to receive some alarm from the SCADA system. And there's going to be some radio coordination, and there's going to go the maintenance team, operation team of the distribution company, and finally they are going to recover the operation of the distribution system. Yes, because of the SCADA, the integration of the SCADA systems to the operation of distribution companies. There have been some other applications to specific microgrids regarding SCADA systems, which is basically, it might be a small SCADA system for a small microgrid with 3 distributed loads. We have loads here and also distributed generators, and there's basically composed of a web interface with some users that are monitoring the system operations. It's an OPC server and a PLC and the local controllers of the generation units. Those approaches are so far good, and the main advantage that they have already is that the examples that I show you are dedicated to specific projects where the operation is in charge of people who is being educated and prepared for the operation of a power system. Of course, the example of the distribution company, and this is basically one small microgrid that might be implemented in a university or on some specific location where the people who's monitoring is people who's dedicated to that issue. So these people take charge of the operation and maintenance of the microgrid, so they won't face too many troubles in that sense. So on the other hand, we have the isolated communities, which is going back to the Huatacondeo example as Luis showed you before. It was an isolated community that at the beginning only had a diesel engine for a power supply, and there was a limited power supply for about 8 hours per day. And later then we convert that small isolated location into a microgrid, which has right now a hybrid system composed by batteries, wind power, PV power, and so on. This is the diagram of the microgrid, as Luis showed you before. Okay, we have installed all the microgrid. The microgrid is completely installed, but we are now facing a challenge. Which challenge is that one? We have to ensure a large lifetime of equipment. We have to ensure low operation costs. We have to ensure low maintenance costs for the microgrid. How do you do that? Basically, there are 3 main aspects when you deal with it. There are engineering solutions, which is basically based on equipment acquisition and designs and construction of equipment. You have also automatic control monitoring approach, which is the SCADA system. And of course, you have to deal with education and training, maintenance, programs, training, outreach of the way you develop the project with the community. But is it enough? to ensure long-term sustainability of the project. It means that the project by itself is going to have a long time life. Can we ensure that? If you not ensure the community participation, you are going to face poor operation, poor maintenance procedures, higher costs, and short lifetimes of equipment. So how can we ensure the lifetime of the project? We are presenting the social SCADA approach. So you are promoting the community participation, and if you are promoting the community participation, you can somehow have adequate operation, maintenance procedures, low cost, and expected lifetime of equipment, as you thought at the beginning of the project. Then, long-term sustainability of the project may be possible. So we came up with the social SCADA. Basically, the methodology, the design methodology for the social SCADA approach, it is composed of the stages that I'm describing there. First of all, we have to make some community characterization, of course, system characterization, design of procedures, communication architecture, how is it going to be developed, the SCADA system, of course, the design of control supervision system, the human-machine interface design, because it's not completely full educated people, so you have to be smart also for the design of the human interfaces, human-machine interfaces, the implementation, and later then, of course, the validation of the social SCADA approach. The elements that are covered by a social SCADA approach, we are dealing with three main issues, which are the real-time operation. In fact, there are, I don't know, real-time operations, maintenance, and also we are dealing with medium and long-term planning support. And each one of these issues, of course, requires some input, which is in somehow depicted over there. For example, for the real-time operations, we are going to require how the decision-making is carried out inside the community. For example, we also have to deal with, of course, the units that are located in the microgrid, the socioeconomic level of the population, and of course the community. And of course we have to decide the supervision of the network and some database storage. In the case of maintenance, which is another scope, we also have to consider some of those inputs that are depicted over there. And maintenance, also the maintenance applications produces alarms as a function of the social structure of the community. And of course we have a maintenance program for the distributed generation units. There's of course a communication architectures and the ways of you have to communicate in order to ensure the maintenance of the microgrid. There are some other applications if you are more ambitious and you are thinking in the long term, as we are doing. There are also applications for the medium and long-term planning support, which is strongly related with a decision support tool. And in that issue, because we're talking about medium and long-term sustainability and medium and long-term planning, we are considering as an input, for example, the signals provided by the Dream Map. The Dream Map is a social application that we did with the people, and we asked them to give us their feedback about how they look, the population or the location in the future after the project was implemented. So we consider those inputs for the long-term planning of the microgrid, for example. In our case, we are on the first steps. We are dealing only with maintenance and real-time operation right now. Of course, we hope to expand the application of the social SCADA, but right now we are basically working in the short term. How are we doing that? For the case of our microgrid, is of course we are adding the social aspects of the community and also the microgrid itself, and that it will produce the social SCADA. So first of all, we have to consider the community, And the community, we are considering the socioeconomic structure, the organizational structure of the community, conflicts and alliances, and the dream maps, as I told you. And of course, it is important to also describe how the decision-making process works inside the community. On the other side, because we are talking about the microgrid, we have, of course, our power system, which is composed of basically three main issues. The SCADA by itself, which is the supervisory control and data acquisition system, the electrical network, and the local resources. Of course, we have to deal with the existing generation units, the system instrumentation, the distribution network topology, and also energy measurement systems, and so on. So, the social SCADA bring up all together. One by side, we have the community, and on the other side, we have the power system. And because the application of the social SCADA, we are having like energy for community system, for community service, and the social SCADA will provide us results for the planning, for the operation planning, for the maintenance, and also for the real-time operation of the microgrid. So the social SCADA possesses tools that support the community in managing and operating the project. These tools consider the following aspects: mid and short-term planning, system operation, real-time operation, and maintenance of generation units. So we join all them together, and now we are our approach, or our approach for energy for community service. Okay, how has been implemented that issue? We are now the communications architecture for the social SCADA application. There's a supervision module, and the controllers get connected to the network through a standard communication protocol. The social SCADA is also connected to an OPC server, and we are storing all the data in a database. This is an example of how the communication scheme is designed for the maintenance module. It's just basically the social SCADA. We are able to send SMS messages to the maintainer. A maintainer is a specific guy inside the community who has to play that role. It is also important to state that given that we are working with isolated communities, we don't have, as the standard SCADA application has, that a specific person who's in charge of the monitoring and controlling the microgrid. So we have to deal with the fact that it's people that also goes to their fields. They have crops and cows and all the stuff, so they are always traveling. They are always in the front of the monitor. So we have to design an application that I maybe join all the community to deal with the operation of the microgrid. And the maintainer, it might be not at the location, but someone is going to identify if there's an alarm or a maintenance procedure request. Well, the communication network for the case of Huatacondeo is the database, which is Matricon. We are also following the IEC communication standard. And for example, our field network is serial based on ERS 485. This is the way the Huatacondeo is organized. We have our OPC server, our SCADA system, and the optimizer that provides the settings, the generation programming, and the generation settings. And we have all the local controllers over there for the different units that are taking part of the Huatacondeo application. And also in Huatacondeo we have a demand response program. I'm going to explain you later how it works. Well, going to Huatacondeo, how we do manage the fact that we are not always with people who are supervising the network operation and maintenance. So what we did, it was the design of a smart blackboard, which is located at the community center. And that smart blackboard is about the size of this board, more or less. And it's a touching screen, so all the people it's invited to go to the community service and they can interact with the blackboard. So the blackboard provides the community about alarms, indicators, useful information, real-time operation of the microgrid. So the people is always interacting with the microgrid and how is it working. And if there's a maintenance task, they just call the people who's in charge of that, and that's the way we are working with the community right now. So we have over there the smart blackboard, which is located at the community service center. And we have our database, our LAN network, which is Ethernet-based, and our field network with the local controllers and the generation units and loads. This is an example, as Luis showed before, how the social scan, so how it's working. The first data that we're gathering is, of course, the operation data. And as you may see, the operation data of Huatacondeo is just basically the orange, the purple line is the consumption of the location, the purple line. The green line is the energy provided by the battery storage system. The orange line is power injection of the diesel engine. So how does it work? Because of the operation of the energy management system and the optimization algorithm, it's just basically that on the first hours of the day, the energy is provided by the battery bank. It's just that these green lines goes under the purple line, but for the first hours of the day, we are providing power supply from the battery storage system. Later then, we have plenty of solar resources, even greater than the demand by itself. So the difference between the solar injection and the consumption of the community is injected to the battery storage. So we are the difference storage that energy in the battery system again. And we just continue supplying the consumption of the town. Later then, when the sunsets begin, and this is like the peak hours of the system, when all the farmers go back home and they just watch the soap opera at the night and all the stuff in Huatacondeo. So basically what we do is, this is the operation of the diesel engine for these hours. The diesel engine provides just not only the peak demand, but also a difference which is required for the final charge of the battery storage system. So the difference is here for the battery storage system, and we are storing, we have, saving energy in the batteries. And how is it? That's the way the microgrid operates in Soho. So we are providing energy for 24 hours for that isolated town instead of 8 hours as they did before. And also, as Luis said, we are achieving diesel savings about 50% of the original consumption of the town. Okay, these are some examples of the design of the smart blackboard, which is located in the community center. This is, for example, you may excuse me, but those are in Spanish, of course, because of the community. And those are announcements. So they can see announcements. For example, there's going to be a meeting on the day 11th February, and location, community center, motive, various, some of discussions. Some other interface of the smart blackboard is of course the power system, so they can see which unit is operating and the real-time operations of the microgrid. We also have social indicators, sustainability indicators, because we are evaluating the behavior of the community in the long term. So we have education level. We are tracking all the grades that the students of the small school of Huatacondeo are getting after they have energy for the 24 hours. Diesel savings, water consumption, security issues. We are also measuring greenhouse gases emission, and the also measurements of how the community incomes in an average level. Some other applications. This is, for example, maintenance. Those are the tasks that gotta be achieved for each one of the applications. The batteries. This is the water tank. That one is the diesel engine, PV, and this is the calendar. And they are also able to send us emails if they have some doubts about the maintenance procedures and that stuff. And this is a funny application, which is the demand response program of Huatacondeo. And the demand response program of Huatacondeo deals with these kind of clocks. Those are 24-hour clocks that are located in some houses in Huatacondeo. We are also working right now with 4 testing families, and they have that clock in their houses. And as you may see, the clock shows the 24 hours of the day, and each slide of the clock has a different color, which basically means if for example here at the 20 hour is green, it is supposed that at that time the system is plenty of energy, so we are inviting all the people to consume energy. If, by the way, it is yellow, just be a little bit careful with the energy consumption. And finally, if it is red, just the consumption has to be for specific applications and no more than that. Just be careful with the use of the energy. So we are sending that signals to the houses, and they are working with the demand response program right now. And for example, this is the generation of 1 unit, and also the way the meters behave and the consumption and all this stuff. That one is the boards I was talking about, and those are some pictures of the training of the population, how to deal with the board and how they have to work with it. This is also a training, but this is that one was developed with the children of the community. Okay, so some conclusions about the social scale approach. This is a novel way for integrating community through SCADA system in projects of renewable energy-based microgrids. The social scale applications considers social aspects for this design. The community is involved with the project and ensures its permanence in the long term. We have validated somehow with some media interviews that they just ask the inhabitants of Huatacondeo how they are dealing with the microgrid operation. Right now we are achieving good results, and the response of the people has been so good. The applications also provides, as I told you, some sustainability indicators that show the community evolution through the time. And the system operation has been stable with 50% of renewable energy operation. And with the social scale approach, we are able to say that the long-term sustainability is feasible. Finally, just full automation of the system. We have to, it is future work. We have to improve our optimization cycles. We have to deal with the security constraints of the unit commitment and the optimal power fall, the set points of the SCADA, automated state transitions for different scenarios. We are working right now with it. And we are also developing a model that supports the decision-making process, considering social aspects like the future visions of the community. Okay, that's it. Thank you very much.